In this video, I want to do several examples of both showing two groups are isomorphic as well as showing two groups are not isomorphic. To start with, let's let C be a fixed element of a group G. We're going to define F going from G to G by F of G equal to C inverse GC. And I want to know, is this an isomorphism? Let's start with showing that this is injective. In order to do this, we're going to let F of A be equal to F of B. F of A is C inverse AC. F of B is C inverse BC. I can multiply both sides on the left by C. When I do, I get AC is equal to BC. I can multiply both sides on the right by C inverse. And when I do, I get A is equal to B. So yes, this is injective. Next, let's show surjective. So let's pick an element in G, and I need to find something that maps to it. Well, if I were to do F of CAC inverse, this would be C inverse times CAC inverse C. My associative property lets me go ahead and regroup this so that I would just have an A. So I have an element in G that maps to every element A. Finally, I need to show my identity. So let's start with F of AB. This is C inverse ABC. And I'm going to write this as C inverse A times CC inverse BC. I haven't changed anything since all I did was multiply by the identity here. Regrouping, I have C inverse AC and C inverse BC. This first parenthesis is the definition of F of A. The second one is the definition of F of B. So I have my identity holds. So yes, this is an isomorphism. Is Z3 cross Z2 isomorphic to Z6? So let's start by listing out these elements to get a better idea. This would be 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, and 2, 1. Meanwhile, Z6, 0, 1, 2, 3, 4, and 5. One of the main things we know about Zn in these cyclic groups that we've talked about is that it is cyclic and it's generated by exactly one element. In this case, 1. So if this is cyclic, it might give us an indication that these are isomorphic. And if it's not cyclic, that would be a good indication that it is not isomorphic. It definitely cannot be generated by 0, 0, since that would just give me the single element. 0, 1, if I tried a group generated by just 0, 1, well, this would give me the elements 0, 1, added to itself is 0, 0, and that's it. Similarly, if I tried 1, 0, the elements I would get would be 1, 0, 2, 0, and 0, 0. So definitely not those. And in fact, it also can't be the 2, 0 case, because once again, there's nothing in this second component to cause the second component to change. So we're down to 2 possibilities to make this cyclic. Let's try 1, 1. Well, we would have the element 1, 1. Added to itself is 2, 0. 1, 1 plus 2, 0 would be 0, 1. 1, 1 plus 0, 1 is 1, 0. 2, 0 plus 0, 1 is 2, 1. And finally, 1, 0 plus 1, 0 would be 0, 0. So yes, this is cyclic. This is my generator. So now we have an idea that this might be isomorphic. But we still need to figure out the actual operation, the actual function. So, one of the nice things about cyclic groups that you should try to prove is that the isomorphism is going to map a generator to a generator. I know 1, 1 plus 1, 1 is going to be 2, 0. This needs to map onto 1 plus 1 to hold my group operation. If I add these two elements here, 1 plus 2 is 0. 1 plus 0 is 1. In order to hold my group operation for my identity to hold, I need to add these two. 1 plus 2 is 3. If I take this 2, 0 and add it to itself, 2 plus 2 mod 3 is 1. 0 plus 0 is 0. Well, that needs to add to double this, or 4. If I were to add 2, 0 and 0, 1, that gives me 2, 1. That needs to add to 2 plus 3, which is 5. Finally, my last element is 0, 0. If I were to double this element, 0 plus 0 is 0, and 1 plus 1 mod 2 is 0. So that needs to go to 3 plus 3, which is 0. So I went ahead and checked some of my operations, and you can double check the rest. Form your two group tables and show that they are the same under these correspondences here. And you will get that these are isomorphic. Is the function f going from r to r defined by f of x equal to x cubed in isomorphism? The first things we need to check are injective and surjective. And I'm not going to write out the proofs to these, but they are both injective and surjective. What about my identity? The group R is a group under addition. So what I want to show is that f of a plus b is equal to f of a plus f of b. Well, f of a plus b, this is a plus b cubed, which if you work that out, that would be a cubed plus 3a squared b plus 3ab squared plus b cubed. On the other hand, f of a plus f of b, f of a would be a cubed, f of b would be b cubed. And these are not equal, so this is not an isomorphism. Another one, is Z4 isomorphic to this group consisting of e, x, y, and xy, where x squared is equal to y squared is equal to xy squared is equal to 1. So every term when I square it, I get 1. Well, Z4 consists of the elements 0, 1, 2, and 3. Since Z4 is under addition, instead of squaring, I would need to double. So I would need to be looking at 1 plus 1. I get 2. 2 plus 2 is 0. And 3 plus 3 is 2. So not all of these squared get me back to my identity, just this one. But not these. In fact, 1 has order 4, since I would need to do 4 times 1 to get 0. The same thing with 3. So these could not be isomorphic because the elements are not of the same order.